The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
And our next speaker is Ronald Klemencic from Magnusson Klemencic Associates. He is the president of his company and also member of ACI 318. And he's going to talk about performance-based seismic design for tall buildings. With that, I'd like to introduce Ron.
Good afternoon, everyone. Thank you for coming to my presentation. I'm here today wearing one of my other hats instead of my day job as president of our engineering company. I'm here actually representing the Council on Tall Buildings and Urban Habitat and the Seismic working group that we have that is a group of structural engineers from around the world who are working together to find some common ground as it relates to performance-based seismic design of tall buildings. And so what I'm going to present to you today is the results of a workshop that was hosted by the Council on Tall Buildings in Shanghai in mid-September. So just about a month and a half ago or a month ago, we gathered in Shanghai prior to the World Congress of the Council on Tall Buildings and worked together for a full day, mostly sharing the state of practice in our various countries and comparing our practices with one another and starting to form a dialogue about how to form a consensus, not that we'll all do it precisely the same, but at least work within a common framework. And it's particularly important for those of us who work internationally and work in countries all over the world to have a more common platform and a more common framework to execute performance-based seismic designs for tall buildings is important. So at any rate, without further ado, we'll kind of get into some of the details. This is really just a summary of what the workshop and what was accomplished. So there were 8 countries represented in this workshop. Many of them, of course, have high seismicity and great interest in the topic and come from a variety of backgrounds. Each one of these countries had one or more representatives at the workshop, and each spent about a half an hour presenting an overview of the practices in their country and how performance-based seismic design is implemented. Specifically, we looked at these areas. I won't read them all. You can read them yourself. I'd say the good news after reviewing these various categories is that internationally, we all share a great deal of commonality in our approaches. While some of the specific numbers might be a little different, there weren't radical departures being promulgated anywhere in the world. There are a few items of note which I'll highlight in the presentation here where there is some divergence, and it causes headache, heartache, and frustration for some if you're not aware of those divergences. But these are the topics that we looked at. Of course, in all countries, there's some basis for the building code. In the United States, of course, it's the IBC, and common to all countries, the local codes have some minimum acceptance criteria and minimum demand levels, etc. And so there's commonality here. I'd say where we start to diverge a little bit is in the seismic design guidelines and codes that are available in the world. There are probably 3 and perhaps 4. I'll say 4. I only show 3 on the screen here, but there are probably 4 that guide seismic design of tall buildings, those being the Chinese code, the Japanese code, the New Zealand code, and in the United States at least, we don't have a performance-based design code. Instead, what we have is the Tall Buildings Initiative guidelines, which are you see on the right-hand side. They're guidelines for performance-based seismic design of tall buildings. This is not a codified document. This is a guideline that was prepared by consensus of many practicing engineers and academics, mostly on the west coast of the US. But here's a divergence in practice around the world, where in Japan and in China, performance-based seismic design has long been codified, and it really is the state of their practice. In the US, we still are working under prescriptive means, and if you are to execute a performance-based seismic design, you follow a path through the code that allows alternative procedures. And so there's an opening in the door in the code that allows us to walk down this path, but the specific language is not in the code, and you need to refer to these other reference documents like the TBI guidelines, or there's another document produced by the Los Angeles Tall Buildings Structural Design Council. I guess further to say that many countries outside the United States, in particular Indonesia, the Philippines, some of the South American countries, use the US codes and guidelines as a substantial underpinning of their local provisions. And so some of the countries outright reference the US documents directly. Others have modified and adopted most of the guidelines or language in those provisions, but have made some local modifications to them, but they largely are based on the essence of the US practices. So moving on. So again, all of these countries all have a similar view on what formulates performance-based design. Someone makes a decision about the performance of the building, and that is generally the owner or perhaps the government or a stakeholder. What are those various goals that are in mind, whether it's just minimum protect life, or if there's some other goals or agenda in terms of protecting property or repair costs. And the engineer then uses their skills to achieve those objectives through kind of rational means of analysis and design. In general, the definition of the seismic demand levels country by country are fairly similar, with the exception of China. China's frequent earthquake, by definition for tall building design, it has a recurrence interval of about 500 years, whereas in most other countries, the frequent earthquake is viewed as a 50-year return period. So this is a significant difference in demand levels, which causes many of the designs in China to seemingly be much more conservative. There is a nuance to this, however, that you'll discover in some of my later comments. The views of inherent damping in the building are quite a bit different from, call it North American practice to Chinese practice. And that helps bridge that gap a little bit, but not close it completely. As far as the extremely rare events, there's a commonality in view on what that is defined as. Usually it's a 2,500-year event. If you're very close to an active fault, say in San Francisco with the San Andreas fault, then there's a deterministic cap put on the ground motion demands, and it works out to be about a 1,000-year recurrence interval. But this is isolated to specific areas that are close to faults. And then generally there's an intermediate earthquake that's considered in some codes. For instance, the Chinese code considers an intermediate earthquake. In the US, in the TBI guidelines, the intermediate earthquake is not recommended to be considered. The view being that we're bounding the solution looking at a service level earthquake and service level criteria, and then the maximum considered event and collapse prevention as at least the primary objective. And what happens in between is shades of gray, so we don't focus on it too much. Performance objectives, again, similar in most all countries, that under this frequent ground motion, 50 years in most, 500 in China, that we're trying to have an acceptable performance level that allows serviceability of the building. The traditional performance levels that are thought of are these four, and in the frequent earthquake, primarily we're looking at immediate occupancy as a acceptance criteria, qualitatively at least, and then collapse prevention, or if you want to put it in very precise probabilistic terms, that there's a 10% chance of collapse or less in the maximum considered event for your building. That's the kind of probabilistic side of the design. And then this intermediate earthquake generally targets a life safety performance, but like I said, the intermediate earthquake is probably the most loosely defined of all. When we do these analyses and designs, and this was a common view pretty much worldwide, that for the frequent and intermediate earthquakes, that most everyone is using a three-dimensional elastic analysis, and these are used to proportion the elements and check the original serviceability. And I pretty much think without exception, the underlying software, of course, it changes from country to country. What's used in China is different software than that's used in North America, than in Korea, than in Jakarta. But the underlying is it's a three-dimensional model as opposed to two-dimensional. It captures all the nuances of mass distribution and stiffness distribution, etc. When it comes to the extremely rare event, that's where things started to differ. In, I'd say, most countries, not all, but 2/3 of the countries represented, again, there was a fairly sophisticated and robust analysis made using three-dimensional nonlinear software and looking at actual strain demands and actual ground motion time histories. And the differences in practice here lie primarily in how many time histories were considered, how those time histories were developed, and then some subtle differences in the modeling underlying. Again, the software used for this varied from country to country. In North America, we use a program primarily called Perform, but the Chinese have their own software, as do the Japanese, and they pretty much do a similar thing in terms of analytical capability, and the results from our comparative design seem to be consistent. A few countries are still practicing using a static pushover analysis, and this was primarily prevalent in Chile. And on the one hand, you might say, well, that's not appropriate because static pushover analysis does not capture higher mode effects in tall buildings, which is true, or it's not easily captured, let's say. And on the other hand, though, in Chile, most of the buildings that are being designed and built are only in the 15 to 25 story range. And so the secondary, second mode, third mode responses are not as important or prevalent. When you get into 40 or 50 or 60 or 100 story buildings, of course, the higher modes, in fact, control the design most often. And so this is where the static pushover is clearly not a tool to use. Foundation interaction is a very hot topic worldwide. It's not well understood. In the US, at least, we're just starting to dabble with this. And what I mean by foundation interaction, this is soil structure interaction analyses, wherein we're not simply looking at the foundation of the building as being fixed, if you will, or pinned to the ground, that we're actually considering the rotation and the softness of the soil and the damping provided by the surrounding soil mass. And this is not generally addressed worldwide, with the exception of in Japan. The Japanese, I think, are probably much more advanced in this regard than anyone else in the world. Probably rightfully so, given the number of earthquakes they have and the soil conditions that they deal with in many locations. So many lessons to learn from the Japanese experience. As we move forward in the U.S. and in the countries who follow U.S. practice, I think we're going to discover and learn a lot more in the coming 5 or 10 years on this topic. Hopefully most of those discoveries will be beneficial, but I'm wary that there's a few gotchas out there that we didn't really expect and we'll be surprised by as we begin to play with these parameters. Damping was also a huge topic of discussion. It's been documented pretty well over the last few years that the degree of inherent damping, especially in tall buildings, is much less than has been traditionally assumed in building design. A traditional assumption in building design is 5% damping. Well-documented actual building monitorings that have happened in Japan, in the United States, and elsewhere demonstrate that the inherent damping is somewhere more in the 2 to 3% range, some buildings even less than 2. But at any rate, a great deal of discussion went on about this, both in the US and overseas, where we've kind of settled as a reasonable place to start is 2.5% damping be considered at the service level. For sure, in China, this is where I mentioned earlier, where they're considering these much higher ground motion demands at the frequent earthquake. They're kind of giving you a little bit of a relief in allowing the consideration of 5% damping associated with that higher demand level. So this is something to note. Furthermore, when we get into the nonlinear time history analyses, what's probably most appropriate is to continue to assume some low level of Rayleigh damping, 2 to 3%, because the rest of the damping that you'll achieve in the building is going to come from the hysteretic behavior of the nonlinear elements. So you may have an effective damping that ends up being 5 or 6% due to the damage caused in the building through the nonlinear response. But to get within that 5 or 6% range, starting with a Rayleigh damping assumption somewhere around 2% is deemed to be the most appropriate approach. Again, China consistently sticks with a 5% damping ratio for their maximum event. Also, when it comes to gravity load resisting systems, in North America this is fairly common practice, as with the other countries who follow the American codes, meaning specifically gravity columns and gravity beams, which are not deemed to be part of the lateral load resisting system, are handled separately and handled as a compatibility check, a deformation compatibility check, whereas China and Japan really consider all elements of the superstructure to be integral in the lateral load resisting system and need to be considered as part of the design. So there's not a gravity-only view in both Japan and China as it comes to building components. Most of the other countries consider the gravity elements separately. This is, again, the South American countries, the Southeast Asian countries, et cetera. We're looking at deformation compatibility, much like US practice. And then when it comes to non-structural systems, things that are components in the building, equipment, support of dividing walls, et cetera, this is not considered in great significance in most parts of the world. The only place where it's really considered regularly is in Japan. In the US and in China, non-structural systems are considered when it comes to important buildings such as hospitals or fire stations, but when it comes to commercial buildings, non-structural components aren't really considered in much detail. What I mean by that is specific calculations for bracing, specific calculations for accelerations of equipment, and looking at the performance of these components under those demand levels. And then kind of near the end of the presentation here, peer review is a common theme throughout the world. It's handled differently country by country and jurisdiction by jurisdiction, but it's commonly performed. In China, there are expert panels. In the US, city by city, they're appointed, generally on a project-by-project basis, but it generally comprises a panel of 2 or 3 engineers, sometimes a practicing engineer and an academic and maybe a ground motion specialist, who will review the design of the engineer of record, primarily because these designs are fairly sophisticated. The analytical techniques are quite sophisticated, and most building officials don't feel they have the technical underpinnings nor the resources to review something of this nature. They're usually looking at code-compliant prescriptive designs, and when you venture into the performance-based world, of course, you're putting the code aside, so to speak, and going down a more detailed design approach. So anyway, in summary, I'd say that the performance-based design is really gaining a lot of momentum worldwide. What was maybe 10 years ago only practiced primarily in Japan and to some regard starting in China, has really taken off, and in the U.S., in South America and Southeast Asia, there are many, many buildings now being designed using non-prescriptive approaches. There is, like I mentioned, lots of commonality between us in our practices, but there are some fairly significant differences to be aware of if you venture out into the world and practice in some of these other locations. The degree of sophistication and rigor that is being used country by country is quite variable at the moment. I'd say that in Japan and in the US, this is probably where the most amount of rigor is given to the analytical side of the process. And the other countries are watching very closely what we do and learning and adapting and applying it to their own local practice. And so finally, where we're going with all of this is our goal as the Council on Tall Buildings is over the coming year or so to take all of this information that we now have and digest it down into a guideline that the Council will publish, which is a best practices document guiding structural engineers worldwide for seismic design of tall buildings. And this is just fresh in the process on the heels of our Shanghai workshop. Anyway, that's what I have. Thank you, Thomas, and thank you all for listening.
Would you like to have questions from the audience to Ron? Yes.
Thank you, Ron. I had one question regarding the question, but are we trying to achieve consistent reliability among the different countries? And on the other hand, you didn't mention low combination, which seems to be one of the biggest differences among countries. I once heard this, and I'm not just true. They always ask me, what's the major component or the major factor that affects the capacity of columns? And everybody starts, of course, talking the materials of this and that, and say, no, it's the code of practice.
Right. Yeah. Fair enough. So on the load factors question, yeah, I guess I failed to include that in the presentation here, but there is wide disparity around the world in terms of the thought as to how we combine the various loads, in particular when you're looking at seismic design and how this is combined with gravity loads in kind of boundary types of analyses where you're looking at heavy gravity loads or lighter gravity loads, etc. It's a topic where there isn't consensus and wide divergence. I'm sorry, what was your other question? It was load factors in the first part.
Well, consistent reliability.
Oh, the consistent reliability. I'd say here there is also wide divergence where in China, the kind of the reliability and probabilistic side of the demand definition is not seemingly very robustly considered. Where in the U.S. practice right now, there's a very significant effort going on trying to create this consistency in the reliability of outcome in terms of at least defining the demand levels in a kind of micro zone basis. So if you're working in Seattle or Chicago or Memphis or whatever, that the demand levels are defined so that you can achieve what's targeted as a 10% probability of collapse in a maximum considered earthquake. This is kind of the underpinning of the ACI 7 guidelines. I think the Japanese are very clear and robust in their definition of that reliability. The Chinese less so. So there is some inconsistency there.
Especially in the U.S., regarding the solar action, we're sort of in the nascent stages, determining how that works. I've read some reports about the use of base isolation systems for structures with lower aspect ratios. Do you foresee there being any kind of potential of using those sorts of systems higher in the
Right. There are buildings in Japan that are built that have been seismically isolated, tall buildings, 40 stories, 50. I think the tallest might be 50 stories. In the U.S., this hasn't been done to date for a variety of reasons. One of them being trying to deal with uplift in with a seismic isolation system is a very big challenge. So if your system has any uplift in it whatsoever, it's very difficult to resolve with an isolation system. I think what's going to happen, probably more than seismic isolation in tall buildings, is a more distributive passive energy dissipation systems, whether it be viscous dampers as link beams, whether it be hydraulic dampers as braces or what have you, that certainly in Japan, now also in Korea, it's coming to the US and probably Canada as well, where we're going to be looking more, in particular on very tall buildings in high seismic zones, looking at passive energy dissipation methods, probably not at the base of the building, but maybe distributed in the height. And I think this is a phenomenon that's coming, to me, the place where it's ripe for that is in China, because their demand levels are so much more strict or so much higher than the demand levels elsewhere, and their acceptance criteria is also very strict. So if you're going to achieve a building design within that framework, kind of absorbing some of the energy in a controlled way is probably a wise choice.